So again, just going through a quick little rundown of what we've done. We started talking about atoms. We talked about the different groups on the periodic table, metals versus non-metals. We talked about the way, what they do when they get together, how they can give up and how they can accept electrons. That got us to talking about compounds. That can go in the garbage, actually. I don't need that anymore. We got talking about compounds, how we have ionic compounds, come up with formulas, how we've got covalent compounds and molecules. We did a little quiz. We learned how to name them. Then we talked about putting the chemicals together so that they can react, chemical reactions. That was the last week that we worked on. Right, we put them together and we let them react and we balance things and we talked about types of chemical reactions. We learned how to write them down. That's brought us to here to now. Now we want to talk about a specific couple of families of chemicals which are very important, and that is acids and bases. So what we want to talk about, just as a little bit of a rundown, what's going to happen in the future. Today we're going to talk about how we can recognize an acid and a base by its chemical formula, and we're going to learn how to name some acids and bases. So we're going to recognize them by looking at their formula. Tomorrow we're going to do a quick little lab, and it's not one that has a write-up. It's really more of one to test things out, and we're going to look at their chemical and physical properties of acids and bases. And then we're going to talk about something called pH, how we measure strengths of acids and bases, and we'll do another quick lab on, measuring the strengths using something called pH paper to test the strengths of those acids and bases. Then we're going to talk about a specific type of reaction that acids and bases can do, and that's called neutralization reactions. And that's what happens when an acid gets together with a base. And then we'll finish it off by talking about how acids and bases are formed, how we can make acids and bases. I've got one more major lab, I guess you could say, that's going to be taking place, I think, on Monday. And then our labs will be done for this unit, and we will be thinking about getting ready for the test, which ideally would be on Friday. Sorry, that won't be on Monday, on Tuesday, because of Thanksgiving going in there. Anyway, then we'll be rolling on towards the test. Okay, so today let's talk about recognizing acids and bases. And let's just put down some definitions here, and we'll talk a little bit about common acids and bases. So you can write that down. You ladies, I assume, are just getting observations at this point, correct? Excellent, good move. Perfect. Are there any more quizzes out there? Okay. Acids are chemicals that release hydrogen ions when dissolved in water. Acids, their formula will start with H. Acids are special chemicals. They're molecules, which means they're made up of two nonmetals, but when you dissolve them in water, they behave like they're ionic compounds. We learned that when molecules end up in water, their molecules don't fall apart, and so they don't conduct electricity. Remember our demonstration with the sugar? We finally found some clean glassware, and we ultimately found that they didn't conduct. Acids are molecules made up of two nonmetals, hydrogen and something else, the other nonmetals. But when they dissolve in water, they actually fall apart, like they're ionic compounds. So they're a special class of molecules that exist as a molecule, but as soon as you put it in water, they fall apart and they almost behave as if they're ionic. So they're a special case. So when this molecule dissolves in water, it will fall apart and it will produce an H plus and a Cl minus. And if we were to check their conductivity, they would conduct because they have ions in the water. That's interesting. I'm smelling cigarette smoke.
Yeah,
I am smelling cigarette smoke. That's exciting. Yeah, we've got some workers working on the roof, and they're not supposed to be smoking, but I think they're smoking. Anyway, let's keep going. So let's just ignore it. Just pretend I'm smoking. Just pretend I'm smoking. It's like the 1950s. Anyway, let's keep going. Listen, please. All right. So they're molecules, but in water they break apart. That's what makes them acids. It's this H+ that makes the acids behave like acids. That's what's common about them. Let me talk about some common acids. This one right here, its chemical name, and we'll be writing it in a moment, is called hydrochloric acid. Hydrochloric acid. Its formula is HCl. Its common name, you can actually go to a pool supply store. You can also get this probably at a farm supply store as well, because sometimes this is used to clean equipment, clean various things. You can purchase this as muriatic acid. All right, so you can actually purchase it as muriatic acid. All right. Pool supplies, you can get this as well, because if you have a swimming pool that has the pH that is not correct, you need to sometimes bring that pH down. You add, like if you're getting the pool ready for the year, at the beginning of the year and the water's all out of whack, they'll say, it's not, it's not behaving the way it should. You can change its pH by adding muriatic acid. Let me ask you some. Do you know of any common acids? Anything that you've come across, right, that you think is an acid or is acidic? What do you think, Shane? Oranges are acidic, exactly. There are actually a couple of acids in oranges. Does anybody know what those acids are that are in the oranges? Any ideas? Chemical name and common name. Actually, common name, I'm not sure what it would be, but you can have citric acid, all right? Found in citrus fruit, okay? But there's also ascorbic acid. Ascorbic acid is also found in those citrus fruits. Ascorbic acid also found in apples as well. These are what we call organic acids. They're huge molecules, but they've got H's that will fall off in the water. I don't know what the formula is. Ascorbic acid, though, is vitamin C. All right? Ascorbic acid is also known as vitamin C. How about some other acids that you might have encountered? Yep. Yeah, vinegar. Excellent. Common name, vinegar. Or for the spelling challenged, vinegar. There we go. If you sound it out, I put an I where the E goes. Anyway, don't judge. Vinegar's chemical name is called acetic acid. All right? And the formula for acetic acid, there's two ways of representing it. The way I normally do it is the way I've been taught, CH3COOH. And in this particular molecule, it's the back H that falls off when it gets dissolved in water. That's what makes acids acids. They have an H that when you dissolve it in water that falls off as if it's an ionic substance. All right? That's pretty good for our list. Does anybody have anything they'd like to add? I'm not going to add it on the list and write it down, but any other ideas? Yep. Lemons would contain ascorbic and citric. All citrus fruit would be the same. That's what kind of defines the way they exist. So that's great. Battery acid, if we're talking about a big car battery, it's called a lead storage battery. It typically has phosphoric acid in it, H3PO4. We'll talk about it later. You don't have to write it down. All right? So all kinds of acids around us. What do you got? Stomach acid is actually hydrochloric acid. Our bodies produce hydrochloric acid in our stomach. That breaks it down. Yep. Okay? Excellent. Good stuff. All right. So let's talk a little bit about naming acids. And we're going to come up with the names for these things. It doesn't have to be a grid. It's just the easiest way for me to kind of present a bulk of information. So you don't have to actually write it as a grid. You can just put formula and name. And yes, this is called the classical name. We actually have two naming systems that we use in chemistry. One of them is from years ago that has been, kind of developed over many years. Then we have a newer version. The version that you use that uses the brackets and the Roman numerals, that's the newer version. It's called the IUPAC naming system. Don't worry about it. We'll talk about that next year. We're going to talk about the classical way of naming acids. So binary acids, binary 2, it means it's made up of hydrogen and a non-metal atom, all right? Binary acid is H plus and the non-metal ion, all right? Two parts to it, okay? And this naming system, when we have binary acids, these are called the hydroblankic acids, because all of their names contain those parts. The hydroblankic acids. And you just did a quiz where I needed to provide you the formula, because I hadn't taught you the name yet. What was this HCl called? Oh, I just wrote it down. That's no fun. And you had it on your quiz. What was it, Marissa? Hydrochloric acid. So they're called hydroblankic acids, and with chlorine, it's hydrochloric acid. Okay? So what would HF be called? Now we're extending it. Yeah, what do you got? Hydrofluoric acid. Okay, and what's the next one going to be called? It's a little bit of a tongue twister. It's quite entertaining. You guys can't hear it, but it's entertaining. She's got some pretty good syllables going. But you're close. Hydroiodic acid. Oh. Hydroiodic acid. Next one. What do you think? Yep. Hydrobromic acid? Yep, hydrobromic acid. Now, the last one is a little different. Again, it's a hydroic acid. And everybody makes the common mistake, so I'm not going to drag you through the painful part of it. Everybody wants to say hydrosulfic acid, right? Getting rid of the sulfur and just putting an ic. But that's not the case. Does anybody think they know what it might be called? It's not hydrosulfic. Yep. Yes, hydrosulfuric. Hydrosulfuric acid. Hydrosulfuric acid. Notice it has two H's, and that's because if we cross over the 2 charge and the 1 charge, we get 2 H's for every 1 S. The rest of them, these are all -1 charge, so when we cross over the 1 and the 1, it becomes just HCl, HF, HI. You'll notice most of them are in group 17, and then we also have this one here. All right? Okay? Also notice that every one of these formula have an aqueous behind it. And that's because an acid is only behaving as an acid if it's dissolved in water. If the substance isn't dissolved in water, then the H hasn't fallen off, and then it's not behaving as an acid. So acids must be dissolved in water in order to be acidic and do their acid work, whatever that is. Okay? All right. One more group of acids here, and these are called the oxyacids. And the oxyacids are, oops, I gotta activate my pen, H plus, and there can be more than one H plus. We'll talk about it in a moment. and an oxyanion. And I didn't call them oxyanions when I first taught you guys. These are our polyatomic ions, right? I don't know if you'll notice our polyatomic ions: sulfate, phosphate, chlorate, carbonate, nitrate. I added one in here as well called acetate. All right, and we'll talk about it in a moment. So what I'm going to show you how to do right now is how to change the formula of the ion into the formula of the acid, and then I'm going to tell you the name of the acid. So you can build that little list, and then we'll complete it in a moment. Now, as I stated a moment ago at the beginning, today we're going to learn how to name a little bit and learn their properties of acids and bases. Well, not their properties, sorry, just their names and how to identify them. Tomorrow we're going to do a couple of quick activities in the lab to discover their properties and look at their pH. They're going to be using droppers just like we did the other day. So please have proper footwear, but we're not going to be using glass. So, you know what I mean? Those are not great, but they'll do, right? That type of thing. So, but make sure we've got our toes covered. It's all going to be in micro droppers and micro trays, so that's not as dangerous as if we've got a bunch of beakers and stuff like that out. So to get the formula of the acid, I'll be patient. So to get the formula of the acid, we're going to be adding H pluses to the sulfate and the phosphate, etc., etc., etc. There's two ways to think about it. You can think as if you're adding the H plus and then you're crossing over the charge with the positive charge, just like we got any other ionic compound. You can actually get it by crossing over. Another way of thinking of it is that you need to add as many H's as the negative charge in order to make it neutral. So this is 2 minus. I need 2 of those in order to complete the molecule. So this formula is going to be H2SO4, and I'm going to put the aqueous because it's not behaving as an acid if it doesn't have the aqueous with it. It needs to have the aqueous so that the H's fall off. So 2 minus 2, I need 2 H's. So how many H's is going to go with the phosphate? Yep, Shane? 3. This is going to be H3PO4 aqueous. Which means with your periodic table and your little table that has the anions on them, the polyatomic ions, you should be able to easily get the acids. How many H's are going to go with the chlorate? 1. This is becoming really obvious, right? Good. That's a good thing. HClO3 aqueous. Carbonate is going to get 2 H's. H2CO3 aqueous. Acetate is going to get 1 H. It's minus 1. We haven't seen that ion before, but it's one that we use very commonly. It is HC2H3O2. And you know what? I've already mentioned this acid. There's another way to write that, and I write it like this. CH3COOH. Yeah, that's acetic acid or vinegar, right? And there are two ways to write it. One indicates the structure of the molecule. Writing it in this method, especially when we get to larger and larger molecules, helps us draw the molecule. It helps us give us a guide to the Lewis diagram of that molecule. It means I'm going to have a carbon with 3 hydrogens single bonded, and then another bond to a carbon, and then some bonds to some oxygens. I'm not going to make you necessarily do that, but we could draw the Lewis diagram using that structure. Okay, and 1, therefore the nitrate gets 1 H, HNO3, and those are both obviously aqueous. I'll stick an aqueous on that. That's what those scribbles are, aqueous. Okay, now let's come up with the names. Even though these molecules look more complex than the binary acids, which are very simple, 2 atoms, the names of these are very simple. I call these the blank-ic acids. They're not the hydro-blank-ic acids. They're just blank-ic. So we simply get an ic ending on these. So if I take the sulfate, it's not hydrosulfuric, it's just sulfuric. It's even simpler than the name for the binary ones. In chemistry, I always needed to come up with ways of memorizing things. And when something didn't make sense, I would always call it an opposite rule. In my head, I'd say, oh, that's an opposite rule. Because you'd think, if I went back to here, you'd think these little simple, tiny molecules should have a simple, tiny name. But they don't. They have a name of hydrochloric acid or hydrosulfuric acid. And then you might think logically, well, look at this big molecule, this H2SO4 should have a big complex name, but it doesn't. It has a tiny little name, sulfuric acid. So the oxy acids have little names, and the little binary acids have the bigger names. Just a little trick to help you memorize it, okay? So also notice, when I change the names, the 8 ending turns into an ic ending. That's also an important thing. So sulfate becomes sulfuric, all right? Phosphate, what do you think it becomes? Again, it's not as easy as just phosphic. Phosphoric acid, yep. Phosphoric acid. Those two are not quite as easy as changing the 8 to ic because I've got to put the U and the O in there. But this one works nice. Chlorate becomes chloric acid. Chloric acid. Carbonate, what's it going to become? Carbonate. What would you like to turn it to? What do you think? Carbonic. We say carbonic, but carbonic would be correct. Carbonate becomes carbonic, but we say carbonic. It's the same letters, just the way you pronounce it. Carbonic acid. Does anybody know where we find carbonic acid? That's another common one we could have talked about. Carbonic acid is formed in carbonated beverages. So if you drink some pop, doesn't matter what kind of pop it is, there's carbonic acid in there. That's what makes it taste so good, right? If you ever watch the Food Network, you should watch the Food Network. To watch the Food Network, they always talk about how it's got to be a mix of the sweet with the sour, and the salty and the savory and all that, and it's the balance. Okay, all right. So if you drink the pop, right, that's sweet, but then it's got the carbonic acid, and acids tend to taste sour, So when you drink the pop, you taste the sweet and a little bit of the sour at the same time, and it burns the back of your throat, and you're drinking as fast as you can, you're like, yeah, that's a good drink, right? But what happens if you let the pop go flat, then all the carbonic acid has left. How does a flat pop taste? Gross. Why does it taste gross? Oh, some people think it tastes good. Yeah, flat pop is awesome. It's not bubbly. Have you noticed that it sometimes tastes really sweet? Almost overly sweet? Yeah, syrupy, which means you might like the sweet pop. Anyway, the reason is you don't have that sour from the acid to cut the taste of the sweet. So now the sweet comes pushing through and your taste is like, it's too sweet. So it's the carbonic acid that gives it a little bit of a sour taste to mix you that sweet and sour. All right. Acetate becomes acetic. Acetic. Acetate, acetic. Acetic acid, which I already wrote down. That's vinegar. That's what's found in vinegar. And it's just sour. Just plain sour. There's nothing with it. Okay. Nitrate becomes nitric. Nitric acid. Nitric acid. Capitals are not a big deal. I put up capitals on a few and some lowercase on some others. Okay, let's talk a little bit now then about bases. All right. So what makes so we know that something that starts with an H, that H falls off and we dissolve it in water, that makes it an acid. What makes then a base a base? And again, I don't know how much you talk about acids and bases in grade 9. Do you do any discussion about it? Nothing? All right. Well, acids and bases are kind of almost chemically opposite to each other. Right? I already alluded to you that we're going to talk about a reaction called a neutralization reaction, and that's what happens when an acid gets together with a base. So they have some kind of a canceling effect. And we'll talk about why that is when we get there. We've seen in our ion list hydroxide ions, and that's the ion that is responsible for bases being bases. All right? So when something that contains hydroxide dissolve in water, the hydroxide is able to move freely, and that's what does the job of the base. So in my example, I have an ionic sodium hydroxide. When it dissolves in water, the Na goes off on its own, and the hydroxide goes off on its own, and it is the hydroxide that does the work of the base. It's interesting because, like I said, acids and bases are almost like opposites, and their danger associated with them are equal. But for some reason, acids are like the popular one, right? For some reason, we all know how dangerous acids can be. Oh, watch out for the acid. You burn yourself, right? If you've ever had a toy that had batteries in it, and you take the back off, and the battery's been there for a long time, and there's that stuff that is coming oozing out the side of the battery, right? And someone says, "Don't touch that." Why? Because it's an acid. It's going to burn you. Right? You're very careful with it. In actual fact, in those types of batteries, that's a base. You didn't even realize it. In a car battery, it's an acid, but in the little batteries, it's a base. So it's still dangerous. It's not as dangerous as you might think, but it's still dangerous. But for some reason, acids seem to be the thing we know more about, but bases can be just as dangerous as acids. Okay, you can get a base burn just as much as you can have an acid burn, right? You can be burnt by both of them, your skin chemically, all right? Let's talk a little bit about some common bases. This is a little trickier because we don't have quite as many common bases. That's why we don't talk about it as much. This one here, sodium hydroxide, and we'll just put it here. Common name is called caustic soda. All right, not like soda that you drink, soda. Soda originates its name from sodium. But anyway, caustic soda. It's sodium hydroxide. Sodium hydroxide, NaOH. All right? Caustic soda is found in drain cleaner. So if you've ever had a clogged drain, a product name might be Drano or something like that. Yeah, it has a very strong base. You want to, I don't normally use gloves when cleaning the bathroom and the kitchen because I just don't do that. But sometimes it says use gloves. When you're dealing with drain cleaner, you want to use gloves. There is very strong sodium hydroxide in drain cleaner. Another type of base that is very common is I'll give you the chemical name, sodium bicarbonate. All right, sodium bicarbonate. Does anybody know what the common use or the common name for sodium bicarbonate is? It's in your houses. It's in your kitchens likely. Might be even in the refrigerator. Yeah, it's baking soda. Baking soda. Now, I'm not going to give you the formula for that. You could figure it out. You can figure it out from your ionic naming, but it doesn't have a hydroxide in it, and I don't want you to get confused. What I'm teaching you is the simplest of simple rules when it comes to acids and bases. By the time you get to grade 12, you will have a completely changed view of acids and bases, but we need to start you somewhere, all right? Another important one is sodium sodium hypochlorite. That is a great name. You'll learn about what formula that is. Again, I'm not going to tell you the formula because it doesn't have an OH in it, but it's still a base, and you'll have to learn more to know why. But does anybody know what sodium hypochlorite is? Again, it's found in your houses, might be found in the laundry part of the world, fairly strong base. Yep, bleach. All right, again, strong base, straight out of the jug, bleach. You really, when I do the laundry and I'm doing the whites, right, going to put the bleach in. I'm terrible for this, but you've got that container, right, we got the thing at the top, and I look over the top and glug, 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 I'm splashing everywhere. I should have safety goggles on, because you don't want to get a drop of strong bleach in the eye. That would really be painful. And every once in a while I see a drop go past my face, and I'm like, whoa. Oh well, I should be careful. All right, so there's some bases, all right? And we're going to talk about naming bases here for a moment. And naming bases is easy. We're going to simply deal with the ionic hydroxides, so you name them the same way. Example. We've already seen NaOH, so that's not very exciting. So let's name this particular one. And again, it's got to be aqueous. It's got to be dissolved. And we'll do one more. And with your periodic tables, you should be able to name those ionic compounds. They're simply the ionic compounds that have hydroxide at the back end. If it's got hydroxide at the back end, it's going to be a base. What's my first one here called, Marissa? Potassium hydroxide, right? It's a potassium with a hydroxide. Potassium hydroxide. And what's my second one called? Yep. Yeah, ammonium hydroxide. Ammonium hydroxide. Common in your houses as well. If you've got a glass cleaner like Windex, its active ingredient is ammonium hydroxide. All right, and you're all kind of looking at the clock, and I'm doing the same thing. And I don't want you to write anymore. I'm just wondering if we've got. No, we're not talking about that. I am going to show you though one thing here online. If you go to our day's work, right? Today is the 8th. I did my little thing on naming acids. There is a little sheet here that has some questions on it. Now, I originally gave this sheet out as part of the note, so you can see the top part of the sheet is part of our note. You've done that top part. No need to do that. But there is at the bottom a little section where you can use what I told you to write the formulas and then write the names, all right? And that's on today's date. So you don't need to print that. You could probably just go online and access it, and underneath our note, you can write the formulas for the following and write the names for the following. Okay? And tomorrow we're going to do some activities. We're going to test for properties of acids and bases, and we're going to test for some pH of some common substances. So footwear that covers your toes, because we're not using glass. Okay, good place to stop.